So exponential functions are defined by the equation that's in the form. So inside of that little box, we're going to put f of x is equal to a times b to the x power. This part of it, this b right here, that's called the base. It's the same thing we talked about when we were doing the last chapter. We said the part that was written to the exponent was the base, and then obviously the other part is the exponent. Now what's going to change in this unit is this is going to be a variable. That's going to be what changes. It's going to be a 2, it's going to be a 3, it's going to be a 4, it's going to be a 5. That piece of it's going to change. And we use exponential functions quite often, especially when we're trying to figure out how much a loan is going to be. If we take out an $8,000 loan, how much interest am I going to have to pay after 5 years? Or how much is it going to cost me, or how much am I going to have left after 5 years if I buy a car? Okay. Or if you've got a bank account or money inside of a savings account, and you put $5,000 in a bank account and you just don't touch it, how much is that going to be worth in 30 years? That's how exponential functions are kind of how those things are calculated. So they're kind of one of these handy-dandy tools that gets used quite often. And there are two types of exponential functions. The first one, if b is greater than 1. So my b value is this highlighted. We talked about that just a second ago. That's that base. If the b value is greater than 1, then the function is what we call exponential growth. So if b, the function, is greater than 1, is an exponential growth function, and is essentially growing. Okay, we'll just say, we'll put it in different terms. We'll say that it's going up. It's considered to be exponential growth if it's going up. So like that example of a savings account. You have a savings account and you just leave it alone. And in actuality, if you take this savings account and if you put like $40,000 in a savings account and you just leave it alone for 40 years, if you just leave it alone for 40 years, a $40,000 investment that you make at like 8%, if you leave it alone and don't touch it for 40 years and it compounds, what we say continuously, it will be worth about $700,000 in 40 years. Okay? So that's what we call exponential growth, where your graph is going to be going up. So an example, just kind of to look at something that's exponential growth, this is what an exponential growth graph looks like. Okay, it's growing over a period of time. And we'll talk about what all these things mean, this 4 and this 2 and all of this. We'll talk about what that means in just a little bit. But that's what a growth model looks like. If the b value is between 0 and 1, the function is exponential decay. So it's decaying, and we're just going to say going down. So if all of a sudden you want to go out and buy a $80,000 car when you graduate from high school, and you want to know what it's going to be worth 5 years down the line, there's a certain depreciation that cars have. They depreciate at a certain rate. Now, there's a huge depreciation at the beginning, and then it becomes a little more constant. But you can figure out what that average distribution is, and you can figure out that $80,000 car after 5 years is probably worth somewhere in the neighborhood of $40,000. Okay? Because it's depreciating over time. So we call that exponential decay, and it's going down. So this is an example of exponential decay, where it's starting in the upward quadrant too, and it's getting less and less and less as you go along. That's called exponential decay. So that's exponential functions. Now, if you look at these graphs, you'll notice all three of these graphs, they get closer and closer and closer to this x-axis. But they're never going to intersect it. You're never going to have an account that's technically at zero. Or you're never going to have a car that's technically depreciated to the point where it's nothing. That doesn't happen. So it kind of, as it goes down, it kind of starts to flatten out and get closer and closer and closer to a value of zero, but it never quite gets there. That is what we call an asymptote line. So an asymptote line. So a asymptote line that's not right. I read it wrong. Sorry. Let's try this again. Erase that or scratch that out. I read it wrong. This should say a line. Let's try this again. A line that the graph gets close to but never intersects or touches is what we call an asymptote line. So a line that a graph gets close to but never intersects or touches is what we call an asymptote line. And it's that line that gets closer and closer and closer to it, but it never hits it. Okay, and that's what we call an asymptote line. Okay, so today what we're going to do is we're going to take those definitions and we're going to look at graphs, and we are going to classify them as exponential growth or decay. And then we're going to talk about what we talk about with the domain and the range of these graphs. So if we look at this first one, I'm going to list my A value and my B value. From the definition up at the top, A is the number that's kind of out front there. And then our B is the part that's being risen to the exponent. So if I look at this example, the 4 is my A value. Right? We'll talk more about what that 4 means tomorrow. It actually plays a big part in graphing this. That's not something we're going to talk about today. My B value is 2. Our key today is going to be this B value, because that B value tells us if it's exponential growth or decay. You don't even need to look at the graph. Well, the graph is going to be there today. If you look at that B value and it's bigger than 1, it's growth. If that B value is a fraction, it's decay. So our B value in this case is 2. So it asks us first, is this growth or decay? So this is a growth graph. So we're going to circle the growth. It's going upwards. The second is the domain. You talked about domain and range at all in here?
Yes.
Okay. Domain is how far a graph goes left and right. That's what domain is. So you start where it's the smallest on the left-hand side, and you continue all the points in between till it stops going left to right. So in this case, our domain is going to go from negative infinity to infinity. And that will always be the answer for these for the domain. Anything in this form, that's going to be your domain. The range is how far it goes from down to up. So you take your lowest value of y, and then you go up with it. So in this case, the lowest value of y that these are going to have is going to be 0. And these are always for the range going to go from 0 to infinity. They're going to go from the x-axis up. That's what 0 to infinity represents. Okay. The next thing it asks is the y-intercept, and that's where this a value is going to come into effect. This a value, that a value tells you the y-intercept. Or you can look at the graph. When you look at this graph today, that's zoomed in too far. When you look at this graph today, this is my y-intercept. If you look at where our graph intersects that, that's at the point 0 left and right and up 4. So the y-intercept for these today, you're just going to be able to look at. In this case, it's 0, 4. But if they're in this form, that's always going to be your a value. But today you get to look at them. The last one, your asymptote line. The asymptote line is the line that it never touches. This is always going to be a y equals. And in this case, today, it's always going to be y equals 0. These three things today are really going to be consistent. They're not really going to change. The only ones that are going to change today are your y-intercept, and then if it's a growth or a decay. Those, I think, are the only ones that are going to change today. So if we look at the second one, we've got y equals 5 times 1/2 x. What's my a value? 5. What's my base? 1/2. So if we didn't see the graph, this b value is less than 1. It's a fraction. So because it's less than a fraction, that tells us it's going to be decay. It's going down. Decay down. The domain, always going to be the same today. It's going from negative infinity to infinity. And if you look at the graph, it just keeps going to the left and it keeps going to the right. The range, it stops at our x-axis and it goes up. So our range for this is 0 to infinity. If I zoom it in, find the y-intercept. 2, 4, it intersects right there. That's the point 0, 5. So our y-intercept is the point 0, 5. And the asymptote line is always going to be y equals 0. Because it never, and if you're looking at, again, that asymptote line means it's never going to cross it. And if you look at the graph, it's not crossing it. Okay. Let's look at the next one. Any questions with that one? Pretty straightforward today. Okay, the next one, we got y equals 1/3 times 5 to the x times 5 to the x. What's my a value? 1/3. What's my b value? 5. 5 is bigger than 1, so this is growth. If you look at the graph, it's going up. Going up is growth. The domain, always going to be the same, from negative infinity to infinity. And that doesn't matter. These are always going to be this one. The range is going to change over the next couple days. It might not always be 0 to infinity, but as that asymptote line moves, we'll adjust it. So the asymptote line is right here. So we could put the asymptote line is y equals 0. This asymptote line is always going to be the first value of our range. So the 0 and the 0, so there's our range. The y-intercept is a little bit harder to tell in this graph. You can't really tell what that is, but if we look at our a-value is 1/3. So the y-intercept for this is the 0.013. And just for reference, just remember that this is essentially it's 0a. When it's in this form, this will change over time. But for today, it's just 0a. So there's the first page of your notes. Any questions with those? All right, so we're on the second page of the notes. I'm going to give you work with a partner. Find a partner that you can work with and actually get these done. I'll give you about this is probably going to take 2 or 3 minutes is all this should take. But work with somebody, help them out if they have any questions. If you have any questions you just want me to individually answer, I'll answer them. But we'll give you just a couple minutes to go through those 4 problems. Okay, let's go. All right, let's go through them real quick. First one, growth or decay. Decay, the domain from negative infinity to infinity, the range from 0 to infinity. What's the y-intercept? 0, 3. My a-value is 3. Asymptote, y equals 0. Second one, my a-value is 2. My b-value is 1/2. Domain, negative infinity to infinity. Range, if you look at it, it's from 0 up, so 0 to infinity. Y-intercept? 0, 2. And the asymptote line, y equals 0. Oh, it's decay. Yep, sorry, we didn't answer that one. It's decay. Third one, growth or decay? Domain, negative infinity to infinity. Range, 0 to infinity. Y-intercept? 0, 5. The asymptote, y equals 0. And it is growth. And the last one. A value is 1/2. B value is 1/3. So we know it's decay. Domain, negative infinity to infinity. 0 to infinity. Y-intercept? 0, 1/2. And the asymptote line, y equals 0. Lots of zeros in this stuff today. Okay. Remember, when we're doing the y-intercept, just real quick, just to kind of remind you, that point right there is the 0.05. That's why it's the y-intercept. Remember, when you're on your axes, you go left and right first, and then up and down. Okay? Any questions? Okay, so we should be able now to take these and find the different characteristics of these graphs. Inside of your OneNote, there should be a tab that says Chapter 7 or just 7. I don't remember what it says. But it does have just 6 questions in it today. Those 4 questions took you about 5 minutes, about 3 minutes. This should take you about 5 minutes. Just put your phones away to the side for a second. Get this done inside of OneNote so I can grade it tonight. I can get it in the grade book tonight or tomorrow, and you don't have to worry about it anymore after today. If you have questions, please make sure you ask.